Today's program, Professor Lakshmi Varagan, Mrs. Varagan, and all the students and students from other colleges. A very good morning to you all. So, my duty is to introduce as well as welcome Professor Varagan for this auspicious day program. The distinguished guest of today, Professor Lakshmi Varagan, George Lynn Cross Research Professor Emeritus, University of Oklahoma, USA. He was graduated from the University of Madras and got his post-graduation and doctoral degrees from Indian Institute of Science, Bangalore. He has worked as professor, as a visiting faculty in prestigious institutions all over the world like Indian Institute of Science, IIT's Brown University, Yale University, and currently he is attached to Oklahoma University. He has traveled through the lengths and breadths of the globe for various academic deliberations. He has been serving as a member of the advisory board of several world-renowned universities in India and abroad. He has been honored with the prestigious awards by the University of Oklahoma for his outstanding contribution in the field of computer science and mathematics. The prestigious George Lynn Cross Research Professorship, it is given in the website of the university. They have written like this: the George Lynn Cross Research Professorship is the highest research and creative activity honor given by the university to a faculty member who has demonstrated outstanding leadership over a period of years in his or her field of learning or creative activity. And the term of George Lynn Cross Research Professor is continuous until retirement or separation from the university. And you can understand the highest award of the university has been received by him for his immense work in the university. He is a fellow of the IEEE, and for a short duration he has been teaching electrical engineering and then moved on to computer science, which he has been teaching and researching for the past 50 years. He has also contributed to the field of meteorology since 1995. And he is one of the faculty of IIT Madras when IIT Madras established the Department of Computer Science in 1973. He is one of the founder of the Parallel Processing Institute at University of Oklahoma with the aim to create the infrastructure necessary to sustain research and training in parallel computing. His current research areas include big data analytics, dynamic data assimilation and its applications, multi-agent dynamics and network science, interconnection networks for parallel computers, learning algorithms, and computational finance. The grants and contracts received by him amounts to $5.2 million US. 33 students were granted PhD degrees and 42 students were granted MS degree under his supervision. He has offered 52 short courses in internationally reputed institutions. He has served as member, chairman, president, and in number of university, college, and departmental committees. He has been the life fellow of IEEE since 2013 and ACM fellow since 1995. He has served as a consultant in Oklahoma Medical Research Foundation, Amaco Production Research Center, National Institute for Standard and Technology, Maryland, and formerly it is known as National Bureau of Standards. He has visited more than 100 institutions all over the world to deliver invited talks in conferences, and to his credit, he has written 7 books, 2 book chapters which has been published by internationally reputed publishers like Springer, Oxford University Press, Cambridge University Press, and McGraw-Hill. He has published more than 100 research papers in internationally reputed peer-reviewed journals in the field of computer science. And dear friends, yesterday GIT has crossed an important milestone in its journey, and we have signed an MOU with IIT Madras on industry skilling for the BTech students of our college. And this is the first of its kind in the state of Kerala, and we are the first institution in Kerala to sign this MOU. Though ours is a budding institution, we strive to strike hard in the highly competitive world with an aim to provide the best and quality education for our students. And we have formed an advisory board for our engineering and generally for GIT, with members from nationally reputed institutions and research laboratories. And Professor Varagan has accepted to be a member of GIT advisory board. Not only mere acceptance, and today he is midst us, and we are fortunate to have him. First, it was planned as a mere visit of him to GIT. So we thought, why not our students shall get a chance to interact with an internationally renowned scholar in computer science. So we requested Professor Varagan for his lecture, and he readily accepted and to give a presentation to our students, and that is happening today here. Thank you, Professor Varagan, for all your support, and expecting more advices and guidance from you in the coming days. As a token of our respect, I kindly request our chairman, George Thomas, to give him a memento on behalf of us.
Thank you very much to the chairman, principal, and my good friend. I'm extremely delighted to be here. I'm going to be talking about gentle introduction to data science that will help you to visualize what is data science, where it came from, is it new? I'm going to argue data science is not new. The name data science is new, but what we consider data science today is as old as science itself, and that's the thesis I'm going to present. Data science began very early. It has its beginnings in astronomy. As anybody in physical sciences should know, astronomy was the earliest of the physical sciences. Anything and everything that happened in physics and other aspects of physical sciences began with discoveries in astronomy. So much of what we know in physical sciences had their origins in astronomy. At that time, 300 years ago, what did they have? Is it too loud? What did they have? They have a handheld telescope. They were able to mark the positions of different planets around the sun. They did not have the paper pencil as we know today, but still they were able to collect data. So data collection began very, very early with observations of celestial objects moving around the sun. So that's the first of the starting point of data science. Thanks to the Herculean efforts of pioneers, Copernicus, Galileo, Kepler, Newton. So the concurrent thought at that time was geocentric. The Earth was the center of the universe, but he proved that heliocentric sun is the center of the universe based on the data observation. So the very first law, the movement from geocentric to heliocentric, began with Copernicus. I would like to come back to the Indian astronomy, which even dates back way back. But before I go there, I want to talk about Galileo. What did Galileo do? The leading tower of Pisa, he dropped a ball and a feather, and he proved that both the ball and the feather are attracted towards the Earth with the same acceleration due to gravity. Okay? It's an absolute law he invented based on analysis of data. Kepler, in my view, is the father of modern data science. Kepler had collected 15 years of data of various planetary objects. He analyzed those data for 10 long years to come up with the 3 basic laws that we all take for granted, namely, the planets move around the sun in elliptical orbits. The sun is at the foci. The most important of the Kepler's law is that a chord joining the foci to the point in the ellipse sweeps equal areas in equal intervals of time. So he discovered these laws as a result of his ingenuity combined with the analysis of the data at that time. When Newton, standing on the shoulders of Kepler, invented the universal law of gravitation. So these are some of the noteworthy developments in data science. In the early days, you can see the dates. So what is the basic idea in data science? You collect data, from data you want to create a model. And that's what's called data mining. So data mining, even though it was not called data mining, is the basis by which scientists have invented, created new laws, new models to explain the behavior of Mother Nature. So early observations suggest the existence of very simple laws of nature. Observations were collected over decades, meticulously analyzed to formulate the laws of nature. The examples include, I have already talked about heliocentric system, laws of Kepler, laws of gravitation, Newton's laws. And these are the basic results within the context of physical sciences that has a current, a flavor of what we now today call data mining. So what is data mining? Data mining is the process of extracting the structure or patterns inherent to the data or observation. Data observation, we use it in the same fashion. They are synonymous. These patterns give rise to clues about the data generating process. The goal of data mining is to understand this data generating process, and it involves going from data to model. Here, Kepler had 30 years of data. He analyzed it for 10 years. He didn't have a computer, he didn't have paper, he didn't have pencil as they do today. With his sheer ingenuity, he was able to extract the three laws which are very fundamental to understanding of the motion of the celestial objects around the sun. And that's one of the earliest of the discoveries that lies at the heart of data mining. Today, data mining includes every area. So there is really interest in data mining. Why? The data is abundant today. It is estimated the volume of data collected doubles in every 2 to 3 years. And why does it happen? And what made it happen? Today we can measure using sensors anything and anything. For example, 15 years ago, 20 years ago, if you had to test whether you have a blood sugar, you have to collect the samples of urine and examine that. Today I can do whether you are having a diabetes problem just by doing the blood test. So we are able to measure things that we couldn't measure. That means we are able to sense the signature of various ailments that affect the human body simply by doing a blood test. We can test for various types of cancers. We can test for various kinds of diseases that affect the human being simply by doing special blood tests. Why? We have sensors that would help to discriminate one versus the other. So, the presence of sensors. Secondly, we have cheap wireless communication devices. I can measure anything from any place and send it to a common place. So, wireless communication in there. Thirdly, we have vast computer storage devices. I can have terabytes of data can be stored very easily. Then I can process this data using very fast computers. So it's a combination of 4 distinct technologies: sensing, wireless communication, storage, and computing technology. These 4 together has renewed our interest in data science. So the volume of data collected doubles in every 2 to 3 years. Today, the data mining, interest in data mining includes all of physical sciences, biological sciences, environmental sciences, banking, commerce, government, and what else. That's why new data science programs are being formed all over the world, because that's part of math. That's part of humanity. I I want to talk a little bit more about data mining a bit later, but I want to go back to the early days of astronomy to give you a broader picture of what data science is all about. So data mining is one part of data science. So what is important here? The development of models. So Newton knew at that time that I want to be able to describe the motion of the Earth around the Sun, the motion of other planets around the Sun. They did not have the tools in mathematics at that time. He felt there is a need to develop a new language in mathematics called calculus. So he invented differential calculus, integral calculus, differential equations. So he in England and Leibniz in Germany, they essentially developed the theory of calculus, differential equations. Once he was able to invent the notion of a differential equation, he was able to explain the motion of the Earth around the Sun. Once they are able to explain the motion of the Earth around the Sun, he could tell at what time the Earth will begin to shadow of the moon. Lunar solar eclipse. He was able to predict the occurrences of lunar solar eclipse using the models at that time. So you can see the importance of models, data to model, data mining. And if you have model, I can make predictions. So prediction and model building are two of the major important components in data science. So with the availability of the models, the potential for forecast or prediction became very clear. Many things we do in life. Okay, now I want to talk about another strand of ideas. Gauss. Is there anybody who has not heard of Gauss? Gauss is one of the greatest mathematicians ever lived. Gaussian distribution in probability theory and statistics. I'm sure you have probably all heard of that. How many of you heard that? Raise your hand, guys. Raise your hands. That's right. That's right. You all know. I'm talking about the same Gauss. Gauss was only 24 years old. He was a young man. At that time, there is an open problem. What is the open problem? The astronomers were looking at an object called Ceres, which is one of the small planetoids. It was revolving around the mother planet, but suddenly went outside. Just like we go outside because of eclipses. But the astronomers did not know the concept of eclipse at that time. So they thought it lost this object. So what was the major question at that time? Where did it go? Then it will come. What bearings it will show up again. So that open problem was taken up by Gauss, who was only 24 years old. So what did he do? He took up all the knowledge that was present at that time. So he fell behind the shoulders of Kepler. Kepler has shown that every planet revolves around the Sun in elliptical orbits. So he knew this planet must be revolving around its mother planet in elliptical orbits. How many of you know the equation for ellipse? That's right. I know you know. Why? I may be working in America, but I got all my education in India. So, Indian system, I'm very thorough. I understand thoroughly. So, you must have done equation to ellipse. Equation to ellipse is a polynomial in two variables of second degree. An ellipse equation is ax squared plus bxy cy squared dx ey and f. So there are 6 coefficients a, b, c, d, e, f. So that ax squared plus bx cy squared, that represents the general ellipse. I'm not interested in the general ellipse. I want to be able to find the particular ellipse that this planetoid was following. So he posed the problem like that. Then astronomers have corrected the positions of this object, Ceres, over a long period of time. So he knew the positions of this planet. He also knew this planet must be revolving around the mother planet in elliptical orbit. Then he thought, why don't I use that data to be able to estimate the coefficients A, B, C, D, E, F. That led to what is called parameter estimation. the model. There was no technique available. He invented the method of least squares. How many of you have done least squares in basic statistics? Raise your hand, guys. I know. Hey, raise your hand like this. I want to see. Yeah. I want others to see who have done. So least square technique is a standard technique in basic statistics. In basic statistics. Half fitting, regression analysis, least square estimation. So he developed, he invented the method of least squares at that time, and using the method of least squares, he estimated the parameters of the ellipse of this particular plot. Then he again fell back on Kepler's shoulders. What did Kepler say? The chords fit equal areas in equal intervals of time. He knew the time at which the planet was lost. So he could forward that and could predict when it will come back. Sure enough, that the first prediction in the context of astronomy then became true. So he was able to predict. So what the contribution? He built the model. He estimated the parameters of the model. He invented least squares. Not only that. So I want to talk a little bit more about this. Now, so 3x squared plus 4x squared plus 5y squared is a particular ellipse. Ax squared plus bx squared plus c squared is a general ellipse. I'm not interested in general ellipse, I am interested in particular ellipse. So using that particular ellipse, and what is that particular ellipse? That's called assimilated model. Assimilation means what? Plant assimilate food. Migrants assimilate in a new society. Assimilation means to become one with. So I have models, I have data, I am trying to assimilate the data into the model. The assimilation of data into the model is called estimation. The estimated model is called assimilated model. That assimilated model is the tool for prediction. So you can see the line of argument now. Data to model, model to estimation, estimation to prediction. These are the basic fundamental steps in data science. So data assimilation involves estimation of the unknown parameters of the model in question. I talked about a problem called inverse problem. I'll come to that a little later. So Gauss in 1801, he laid the foundations of data assimilation. Data assimilation is essentially that his work led to the development of least squares as we know today. Please understand, we have been talking about method of least squares in 2024, but it was developed in 1801. The same method. By the time he also, so he was to use the data to estimate the parameters. In those days, there was nothing else other than the handheld telescope, and there in whatever form they represent the data, but the data can have errors. So he knew the data inherently had errors. He wanted to analyze the distribution of errors in the data. So to be able to explain the distribution of errors in the data, he invented the notion of Gaussian distribution. How many of you are aware of Gaussian distribution in basic statistics, basic probability theory? You will do. If you don't know, you will do. If you know it, you have already done. What are the basic aspects in probability theory and statistics, which is the foundation for data science? So Gauss made a successful prediction on the variance in the time of the reappearance of the lost object. So he developed, look at this now, Newton developed calculus. Gauss developed least squares. Gauss developed the Gaussian distribution. Necessity is the mother of invention. You want to do certain things, you don't have it, you invent it. That's how data science progresses right from the early days. So what is data assimilation? Data assimilation is called the fusion of models with data. Now, I want to talk about a couple of things now. Models are our conceptions of the Mother Nature. We never understand Mother Nature perfectly, but we can only sense Mother Nature through observations. For example, if you are not feeling good, you go to your doctor, you explain what you are suffering from. Does the doctor ask for blood test? MRI and so on. There are observations of the conditions of the body, and based on the observation, the doctor then models what the problem could be and what the problem is, and then tries to write prescriptions to be able to get you back to the problem. Data to diagnosis to cure. That's what every doctor does in every day. So doctors do data simulation, data mining every day in their office. So I want you to think that computer scientists and data scientists are not the ones who do data science, do the data mining. It is done in everyday life. So there are other ways in which data science has been practiced over the years. I just want to expand your knowledge and understanding of the basics of data science. So by combining models and data, we can get specialized model called assimilated model. And using the assimilated model, I can create good prediction or forecast. The standard tool for fusion of models with data is called method of least squares. So least squares method is your foundation for data science. Now I would like to talk about many things we do in life is driven by the need for prediction. Why do we do data science? Because I want to be able to predict it. So there are many things in life depends on the need for prediction. I'm going to give some examples. There's a hurricane brewing in the Bay of Bengal. The hurricane probably grows south of Andaman at the eastern edge of the Bay of Bengal. It tries to move westward. When it tries to move westward, it can go to Chittagong, which is due north, or it can go to Visakhapatnam, it can go to Chennai, it can go to Malaysia. So the angle is very large. We can't stop the hurricane, but we want to be able to forecast where it will land. Why? It can cause loss of life, both animal and humans. We can't avoid loss of property. We can't stop it. So there is a great need to be able to predict the motion of a hurricane to save lives, and that happens very often all across the globe. That a crime has happened, there's a bank robbery, for example, the detectives come, they take data from the crime scene, and then they try to analyze. So every detective work is data mining. From data to be able to understand who are capable of being able to commit this crime and being able to solve the crime. NTSB, National Transportation Safety Board. I'm trying to give you examples besides us, who are all the people who do data science, data mining, data simulation, prediction, and so on. NTSB is a National Transportation Safety Board. Air travel is the most secure form of travel. On the road on a given day, there could be 500 people who may die on the road across the whole of India. That happens in USA, everywhere. But then people die in the distributed fashion, one here, one here, one here, one here. We don't get it. But when a plane crashes, that becomes a big news. Because currently a lot of people suffer at one particular point. So suppose the plane don't crash too often, but suppose it does, what do? The engineers from NTSB go collect all the debris and they try to reconstruct the plane from the way in which it prevents the reconstruction of the original size. They find out there's a metal shear this way, there's a metal shear that way. They try to analyze the cause for the failure. So from the data to the cause, let's take it back. So every detective, be it a crime scene investigation or be an accident happening, trying to find the cause of it, they do data mining, they do data, they do prediction. The next one is an important thing. Let's take national government, state government, your city municipality. Every government needs to develop a plan for the next year. For example, Kerala government has to decide how many crores they are going to spend on education, how many crores they are going to spend on roads. So they have to develop budget priorities. To develop budget priorities, they need to know how much money they will have in the finance department at the start of the year waiting to be distributed. So be able to predict the total tax revenues that the government can have to be able to develop budget and policy. The government runs because there's a group of economists predict they will have this many crores coming into our banks. Of course, I talked about medical diagnosis already, from symptoms to the cause to the cure. Every doctor predicts what you are suffering from. Are you there? More often than not, the prediction comes true. In some cases, they miss it. If they miss it, they try to do some trial runs, and then they adjust and come back. So this should give you an idea that much of what we do in life depends on prediction. Prediction is fundamental. To be able to predict, I need model. To get the model that can be used for prediction, I need to do estimation. The model itself comes from data mining from data. Now, do you understand the role of data, the role of estimation, the role of prediction? That's where the essence of data science lies. Now, I would like to talk about some mathematical aspects of data science. We all know that there is a system, there's a model, there's an input, there's an output. Right? Our body is the model. You eat food, then input. What the output? Energy. Right? That's right. Your body is related to energy. Growth. Everybody? That's right. So, you can think of model, input, output. Suppose I give the input and the model. The problem of computing the output, knowing the input and the model, that's called a forward problem. So when you are in college, you learn to solve forward problems. That's what all your teachers teach you. How to solve a differential equation, how to multiply two matrices, how to be able to estimate the acceleration due to gravity, how to estimate the pressure constant for air, so on. But sometimes I may know the input, I may know the output, I may not know the model. For example, you are suffering from something, they set an X-ray, they get the output. So you know the input, you know the output. Knowing the input and output, I want to be able to model mine. Yeah, that's the factor here. Okay? So every X-ray tells you what is the input, what is the output. From the input and output, I'm going to guess what the model is. So that's why. Sometimes I may know the model and the output, I may want to compute the input. So there are three people here, input, model, output. Knowing the input and the model, computing the output is called forward problem. Knowing the input and output, computing the model, that's called inverse problem. Another level of inverse problem is that knowing the model and output, what could have been there? We see three different kinds of problems placed. The two of them are inverse problem. One is a direct problem. Data mining is an inverse problem. Data estimation is an inverse problem. So, mathematically speaking, data science involves solving two levels of inverse problem, one at the data mining stage and another at the estimation stage. Once you solve two inverse problems, the prediction is the following problem. That's the mathematical concept of data science. So what is one area where all these things are depicted very well is called time series analysis. So what is the time series analysis? What is time series? The amount of rain that falls in Kottayam in 24 hours, every 24 hours. Somebody has a measurement. So I would like to be able to build a model to be able to predict how much rain I will have next week, next 2 days. I need to be able to make prediction. Please understand, our life depends on the meteorological prediction they develop every day. Yesterday I was just time in Cochin. Cochin had a huge rain, but they had predicted very well. So what did they say? That would be 15 millimeters of rain. In Cochin it was actually 55 millimeters of rain happening in 3 hours, the probability of that happening is over 95%. This is are you able to absorb the prediction level now? So they talk about the level. What is the level? The level is 50 millimeters of rain. What is the confidence? The confidence is 95%. What is the duration? 5 hours. Within the next 5 hours, there is the potential for 50 millimeters of rain with 95% confidence. That's the product ultimately data scientists have to generate. That's how prediction is. So weather prediction is for public consumption. So weather prediction involves all aspects of data science. All aspects of data science. So I hope you have a mathematical way of understanding what data science is all about. So what are the 3 pillars of data science? Data mining, that's an inverse problem that relates to going from data to model. So when you do data mining, I want you to remember Kepler. Kepler is the master of data mining. So when you do data mining, you are doing something similar to what Kepler did 300 years ago on your data. Data simulation is also an inverse problem that relates to estimation of parameters. Remember Gauss. Gauss was the first one to be able to estimate by introducing the method of least squares. Prediction is a forward problem. So data mining, data simulation, and prediction, they form a continuum and form the 3 pillars of data science. Form the 3 pillars of data science. And then I would like you to ask questions. I don't want this to be a monologue. If you have any question, please stop and raise your hand. We will be delighted to have you discuss. Thanks. If there are no questions, I want to continue. How much time I have? Early days of astronomy. I talk about Kepler, I talk about Copernicus, I talk about so many people. But Indian astronomy, Indian astrology was in a very high state of development. In India, we measure time in terms of yugas. Krita Yuga, Treta Yuga, Dwapara Yuga, and Kali Yuga. Ramayana happened in Treta Yuga. It is estimated to happen about 7,000 years ago. You can debate about whether 7,000 or 8,000, doesn't matter, but several thousand years ago. That's what's more important. Mahabharata happened about 5,000 years ago. There are evidences to all of this. Why am I mentioning this? The horoscope of Rama is supposed to be the model horoscope. I'm not asking you to believe in astrology if you don't want to, but that's not the point. The point is the following. Look at that. They knew the position of Sun, Moon, Jupiter, Saturn, Mars, Venus, Rahu, Ketu, everybody. We talk about heliocentric system, depends on Copernicus 14 something. But we knew this thousands of years earlier. But this fact has not distilled itself into our textbook, even in India. Okay? So we had a very sophisticated understanding of astronomy. We had a sophisticated way of understanding, doing data science, data mining. Ask yourself, 7,000 years ago, how they were able to assess the position of Sun in the 12 sectors in the sky. Okay? It amazes you what kind of instruments they may have used. How did they measure the positions? The relative positions of various planets and objects. Great astronomers of Kali Yuga, and this is given in Valmiki Ramayana. Where is this given here? This is a part taken from Valmiki Ramayana. This is something in our own time, Kali Yuga. Aryabhatta is considered to be one of the greatest of astronomers of all times. He knew Earth was spherical. He knew the Earth revolved around the Sun, and he was able to calculate the average length of the year to be 365. And that happened in 4th century, 5th century, 6th century. That's way earlier than 1471, Copernicus. Then I'm trying to list some of the names of great astronomers from India: Varahamihira, Brahmagupta, Bhaskara. There are a whole host of scholars who make lasting contributions to astronomy and mathematics. Unfortunately, even in India, we don't know much about their contributions. Why? India was never an India. We had probably over 250 kingdoms. Each king, they supported fine arts, scientists and everything else. And these scientists, Aryabhatta and everybody else, they wrote all their findings in shlokas in Sanskrit. It was not written in the modern language of mathematics. It was not readily available. And further, the local kings, and there was no journal to publish this at that time. So what is known remained local for a long time. Only recently, for the past 50 to 100 years, people discovered these gems hidden in Indian literature, Sanskrit literature. They are trying to bring it out and translate them into English literature, and to see the depth and breadth of contributions to astronomy and mathematics by Indian astronomers and mathematicians. Are you with me? I talked about models. I want to give a little bit of feeling about the types of models. To some of you, this may be a little advanced, but I'm sure there's a mix of audience. Others may enjoy it as well. Models, there are two types of models. One is based on causality and another is correlation. Causality means what? If there is force, there is acceleration. Everybody knows that, right? Basic physics. Every Newton's first law, second law, third law. They are all examples of the notions of statements about causality, cause and effect. Not all models are causal models. Some models are also called empirical models or correlation models. What is correlation? If you consider identical twins, they say the same thing. Have you noticed that? Come on, guys. Twin brothers, twin sisters, your twin brother and sister. They're twins, they think alike. They are wired in a similar way. So what does it mean? There is excessive correlation between the thought process between two twins. But between brothers and sisters, there cannot be too much of correlation. So what is correlation? If what I say, what I think is related to what you think, what you say, then we say that's a correlation. Correlation can be positive or negative. Positive correlation means we think alike. Negative correlation means we always think opposite. Okay? To be able to make prediction, there are only two things we need, either causality or correlation. Without causality or correlation, we can't make prediction. And why is prediction important? Please understand. The ultimate goal in data science is to create prediction. Many things you do in life depends on prediction. Why do you want to do BS degree in data science or computer science? That the prediction, if you got a degree, you will get a good job. It is that prediction propels you to go through the rigmaroles of 4 years of training. Are you all with me? I want to think about why are we here? I'm glad you are all here. I'm not asking you, but I want you to think about it because you want to follow your dream of being able to have a good, enjoyable life, to make good money. The only pathway to do that is education. So that's prediction. There's a great correlation between your financial status and your educational status. That's a great example of correlation. Is there a model that generates it? No. There's no causal model, but there's a lot of correlation. So correlation. Model can be explicit or implicit. These are some of the more sophisticated aspects of the model, but as far as we are concerned, I would want to think of causal and correlation as two different attributes of the model. I don't want to belabor this final distinction is slightly more advanced, but then it should be enough that models comes in various forms and shapes. I come from an applied mathematics discipline. I am interested in all types of models, but in your specific area, you may have models like causal, explicit, dynamic model. How many of you have done calculus How many of you have done differential equation? Good, wonderful. Then I can talk to you. So what is a dynamic model? A dynamic model is always defined by a differential equation. What is the deterministic model? D by dx is equal to a times x. That's a dynamic deterministic model. What is a stochastic model? A stochastic model is there is something that is random. The pressure at 10 o'clock in Kottayam, 10 a.m. in Kottayam, is not exactly the same every day. Around it varies. So there is a natural variation of pressure in Kottayam at 10 o'clock every day. So that's a natural variation. That variation is called stochastic. Okay? Random stochastic. An explicit model, implicit model. An explicit model is given by standard differential equation. Implicit model. How many of you have heard of neural networks? You probably do it as you go by. A neural network is an example of an implicit model. So model comes in various shapes and forms. As you progress through your training in data science, you will talk about, if not all the aspects of this classification, but many aspects of this classification. Now, we are talking about data science, so I need to know in what form data come. There are essentially 4 distinct ways in which data can be organized. One is called the time series. The daily maximum temperature in Kottayam at noon. Day by day. The average, the total rainfall in 24 hours in Kottayam. Day by day. The IBM stock price. The exchange rate between dollars and rupees. Am I giving you an idea of the time series? The number of deaths in the highway in Kerala. The number of deaths in highways in India. That's time series. And where do you want to analyze that? I want to find out where crashes happen. Why that crash happens. I want to be able to make sure the places that more crash happens, safer place for drivers. So I want to be able to analyze and cure the problems. So that's time series. So one form in which data arises is in the form of a time series. The next form is called spatial data. During COVID time, we wanted to find out what is the extent of infection of COVID across India, across Kerala. So I'm interested in the spatial distribution of an infection. It is confined to this area, it is confined to this area. When you go there, they are masked, be careful. So that's how they are trying to be able to alarm the public. So spatial distribution of any infectious disease is of great interest for the safety of the public. So data in the form of spatial. The next one is called spatial temporal. Monthly rainfall in each of the state, each of the capitals across the whole globe. There are well over 270 countries in the world. Each country has a capital. I would like to be able to understand the total amount of rain that falls in each of the capitals across the globe, month by month by month. So there's a spatial distribution, there's a temporal evolution. So that's called spatio-temporal data. Time series, spatial data, spatio-temporal data. The last one is in the form of a matrix. How many of you have been introduced to the notion of matrices? Geometry, analytical geometry. Come on, guys. Probably, you'll get it. So, think of it. I have n objects. N objects have attributes. Now, let's talk about this now. I want to be able to, when you go on the roadside, let's suppose you are native of Kerala, you go to Cochin. Cochin has people from every part of the world, right? By looking at this, oh, he looks like a Chinese. Let me say that. Hello, hi, how do you do? You have the ability to discriminate the features features of a Caroline from the one from Nepal, the one from Japan, the one from South Africa. So that's what's called pattern recognition. And how do you do that? You have in your mind an image of how a Caroline looks, how a non-Caroline looks. If a non-Caroline means how an Assami might look, how a Chinese might look. You may not be able to verbalize, but you do know there are features that distinguishes one group of people from another group of people from another group of people from another group of people. That form of data is the matrix form. So X1 could be a Caroline, his features. So what are the features? Height, weight, color of the skin, color of the eye, educational status, salary, animal status. So these are all the features of a person. So if I consider a group of young people, I measure each of them along the same attributes. Everybody? I get an array. Each person corresponds to a column. All of you think? The first row corresponds to the weight of everybody. The second row corresponds to the height of everybody. The third row corresponds to the eye color. The fourth row corresponds to your educational status and so on. So that kind of arrangement of data is called matrix data or data matrix. In all of data sciences, when you talk about data, data has to be in one of these forms. Just like the models in data science has to be one of those models that I talked about in the previous slide. So I would like to be able to provide you a comprehensive picture of the set of all models, the set of all data. So this is what I just finished talking about. So if you are going to be deeper in data science, you may be interested in analyzing time series data, spatial temporal data, or data matrix forms. So I simply argue that data science has been around for a long time. So what kind of tools did they use to promote data science in their own discipline? Astronomers did data science in their discipline. Medical people do data science in their discipline. Statisticians develop data science in their own discipline. So data science is a science that is common to any and every science and engineering. Wherever there is data, there is data science. Wherever there is data, there is model. Wherever there is data and model, there is a need for prediction. So data science is all embraced. So one of the tools that we today in data science have to use, we are going to reuse the same tools that people have been using since the days of Kepler and Gauss. These are coming from statistical estimation theory, multi-data regression analysis, data reduction techniques, classification using clustering, association groups, decision trees, probabilistic network, genetic algorithm, random field. These are some of the things that you will learn as you progress through your curriculum. Okay? These are the tools by which they are going to. Once you learn these tools, you are ready to do data science. You are ready to do what Kepler did. You are ready to do what Gauss did. Remember? So you want to become like a Gauss, you want to become like a Kepler. And these are the tools. These are the mathematical tools. Now, I've been very steadily progressing towards. I talked about what is data science, what is data simulation, what is prediction. Then I talked about models. I talked about various forms of data. Now I'm talking about various methods used within data science. Are you getting a more and more complete picture of what data science is all about? That's the idea. So summary. Data mining seeks to uncover the structure of patterns in the data so that I can summarize the intrinsic properties of data generating process by the model. I can keep collecting data about the motion of the earth around the sun for 100 years. It doesn't mean much. But if I can, in my laboratory, describe using a model the position of the earth around the sun, and generate the same data that Mother Nature gives you, then I have understood Mother Nature very well. All of data science, they strive towards understanding Mother Nature. At that end, I want to be able to summarize the data generating process. And that's what doctors do. Your symptoms is generated by some disease in you. Symptoms are the external evidence, but there's a cause inside. And doctors model that cause. If I can model that very well, then I know these kinds of deficiencies in the body should exhibit itself in these forms of specific observation. So I can model what's going on in your body. If I can model what's going on in your body, I can diagnose it very well. If I can diagnose it very well, I can cure it. That's the fundamental aspects of data science. So the goal of data assimilation is to fit the model to data. That's estimation. That's largely statistics. It's largely statistics. So who are all the people who are doing data science before the data science department came into existence? Statisticians, astronomers, physicists, chemists, doctors, detectives. They have been doing this. But the name data science is a cut-to terminology to emphasize the underpinning aspects of data analysis in each and every instance. So, data mining, data assimilation, and prediction, they form a continuum. They form the three pillars in the development of predictive science. Please understand the notion of predictive science. Ultimately, data science helps you to develop predictive tools. So the notion of predictive science is important. Notion of predictive science. With that, let me conclude. If you have any questions, I hope I have succeeded in giving you a broad overview of what data science is all about. So what is the difference between data science and computer science? In computer science, we talk about basic things: hardware, system software, application software, algorithms, formal languages, compilers, operating systems, the various things that make computers work. But what are the fundamental aspects of data science? What are the mathematics that are required to pursue your career in data science? Linear algebra, probability and statistics, good facility in programming, optimization tools and techniques. These are the tools in data science. Please understand, computer science is a handmaiden of all sciences. Physicists need computer science. Physicists need to do computation. Chemists need to do computation. Everybody needs to do computation. So the aim of computer science is to enable you to be able to solve your problem faster, large-scale problem faster. But data science relates to collecting data, modeling data, specifying the parameters of the model. I hope that helps you to distinguish between what computer science and data science is all about. With that, let me conclude. Thank you. I'll be delighted to take any questions. To how many of you what I talked about is new? Raise your hand, guys. That's right. Yeah. Hey. So what is the aim of these kinds of lectures? Just to tell you the broad picture of what you plan to do in a wider perspective. So from now on, once you can decide whether you want to do computer science or data science. It's your science, you did it. You need to know what is it, why am I doing it, what is my interest in that. Isn't it? How many of you are undergraduate students? Undergraduate, B. Are there any master students? who did not raise the hand for either of that, where are you from? What are you? So you are an undergraduate student, sir? Outside this college? I'm glad you're all. Over to you, sir.
My name is Fiona. I want to know how data science is related to artificial intelligence.
Very good question. I didn't go into that.
Thanks.
Do you know what artificial intelligence is all about? That's I understand. I don't want you to feel intimidated by my question. I want to find out where you are so that I can appropriately answer to make you understand. So what is artificial intelligence? This is a question I'm going to ask myself today. If you can make machines do what humans are doing routinely, if the machines can mimic what humans do routinely, that process of being able to transfer the human ability into the machine, that process, that sign is called artificial intelligence. So what is machine learning? Machine learning is a part of artificial intelligence. There are too many terminologies that come into play. Machine learning is it bigger, artificial intelligence is it bigger, machine learning is a part of artificial intelligence. Now machine, if you talk to a mechanical engineer like him, to him the machine is lathe. The idea of hardware machine, that's what mechanical engineers do. Here, the machine can be a software. The machine is supposed to help you do several things. If a software can help you to mimic what humans do, it is trying to play a role of a machine. So you can represent machines in machine learning to build it as a hardware that's called neural network. You can build it as a software that's called expert system. So when you say machine learning, it could be a hardware based, it could be a software based. There's not much of a difference between machine learning and artificial intelligence. These are fancy terms to represent different stuff. We can argue forever. This is bigger, it's one. So what are the topics in artificial intelligence? The following. A 2-year-old child can distinguish between a dog and a cat. Any dog, any form of cat, a 2-year-old can distinguish. Okay? Has it seen all dogs? Has it seen all cats? So, a 2-year-old understands the overall profile of a dog, a cat, and how a dog and a cat differ from each other. The whole question is can you write a machine, can you develop an artificial neural network to mimic this act of a 2-year-old? So what do? You present pictures of dogs to the machine and tell them this is an Alsatian, this is a German Shepherd, this is that, and so on. And you want to make the machine learn to be able to distinguish between a German Shepherd from other breed. So this aspect of being able to use the human power into the machine is what artificial intelligence largely talks about. So what is the data that you are going to give into the machine? The pictures and representations of dogs. And the information that this dog is an Alsatian, this dog is a German Shepherd, this dog is a street dog. So you provide them an instant and a classification, an instant and a classification, an instant and a classification. You want the machine to learn to mimic a 2-year-old. Can a machine beat a 2-year-old? No. Why? A 2-year-old can generalize. You take it to any place, or she or he, you can distinguish the dog from a cat. It has only seen certain features of certain kinds of dogs. So the machine will make more error than the 2-year-old child. So what is the general topic in artificial intelligence? not only teach a machine to identify dog from cat, to identify different brands of dogs, it doesn't have the ability to generalize in the same fashion like a child. Right? So, it's a part of data science. Why? You have to give this input data and train them. That's what's called learning with a teacher. That's called supervised learning. You learn to cook. Somebody tells you, a mom tells you how to cook. You learn to swim. Your swimming teacher tells you how to float. You learn to play cards by looking at good card players. So most of the things that we learn are learning with the teacher. So you are the teacher who is going to teach this device called neural network to be able to mimic it. So in my estimation, data science is a bigger umbrella, artificial intelligence, machine learning, parts of it. Does that answer the question?
My name is Shreya, and so many of us are here in BTech data science course itself.
Yeah.
So, but common knowledge that we are lacking is that so since we are taking BTech in AI, we don't know what kind of job opportunities or which country we should. For me personally, I like to go abroad.
That's
So,
to become a good data scientist, you need good mathematical training. The mathematical training I gave an indication. So what is the good prerequisite for being a good data scientist? Calculus, linear algebra. You know what it is, right? Everybody know what linear algebra is? If you didn't know, you'll learn it very soon. That's what they are going to do. The principal is going to make sure he is going to grind you through all of this. Linear algebra, probability, statistics, optimization theory, ability to program. So those are the basic fundamental mathematical tools you need to become a data scientist. And it's no different. What does it take to be a good cricket player? What does it take to be a good swimmer? What does it take to be a good musician? What does it take to be a good data scientist? So the curriculum that they have developed is consistent with the university requirements. The university has very thoughtfully designed these courses by experts, and they know the system of courses they need to do, and by the end you come to the fourth year, you will have many different aspects of your theoretical abilities. So by the time you blossom to the third year, fourth year, your knowledge of data science, your knowledge of basic tools will be very broad. You will be able to take on good projects as internship, research projects. So tell me what you are doing. You are a master's student or undergraduate student?
undergraduate student. Pursuing BTech in data science. So my plan is to go to Germany and settle there with data science. So I wanted to ask you some advices on what country you would recommend.
But you are within the university system. You are not going to do what I said. You are going to do what your university requirements said. So that every university has certain requirements to be able to get a degree. So my suggestion is, don't talk to anybody. Understand what the university says. Do whatever being taught to you. Do it very well. And the university syllabus from Madras University may change from here. Don't worry about this. But by and large, they are all very similar. If there is something good, everybody finds out, right? So there is no secret. So all the good things have already been incorporated into the formation of your 4-year syllabus by your mother university. And you are working within the umbrella of the mother university. So mother university has taken the responsibility to make you a good data scientist. And that mandate is to be able to follow that, and that's exactly what they will do. So stay with the college, understand the courses, do very well, you have a bright future. IIT Madras, and he just told me that there are experts from IIT who will be teaching courses in AI, data science, and so on. So your future looks very bright. Your future looks very bright. I went to school just like you. Any other question? If there are no other questions, I don't want to keep. I don't want. Oh, go ahead. I'm sorry. Go ahead.
My name is Arun Babu.
Yeah.
I'm from the Department of Mechanical Engineering.
Yes, sir.
Okay. Then I heard that in data science, we use the technique of statistics, mathematics, and even from the computer. Okay. Nowadays, I heard that is neural network and deep learning techniques. There are two main things in AI. In data science, which is more used, I think the classification or the application of this, or where the neural network is used and where this deep learning technique is used. I heard that for solving these complex problems, this deep learning technique is used. Can you tell us some example to classify the use of these techniques in data science?
Well, that's exactly what I was trying to talk about. So, you are interested in a particular question? Tell me restate your question once more. I want to understand where you are coming from.
Okay, I'm from mechanical.
Okay, I understand that.
Where this deep learning, can you tell an
Oh, I
example?
see. Okay, good. You remember? Yeah, thank you. You remember I talked about two types of learning? Learning with a teacher, learning without a teacher. There's a proverb in Tamil I want to tell you, and then somebody can translate in Malayalam. If somebody wants to climb the coconut tree, how far can you hold him? He has to learn to climb, right? I can only probably hold him as tall as I am. The coconut tree is 100 feet tall. I can hold him only for the first 6 feet. The rest of it he has to climb. So the courses, the BS courses, the master's courses provide you that little push. But then after that you have to learn to climb. Same thing with you. So the college degree provides you with the basic fundamentals. You go to work in an industry, you may be asked to solve a problem that you may not have solved. So you need to be able to utilize all the knowledge you have gained to synthesize a new method for solving that. That's the first one approach. So self-learning beyond college, continuous learning beyond college education is always in the system. BS is only a starting point. Your master's is only a starting point. PhD is also only a starting point. They are not the end. They are the beginning. Second, you asked about deep learning, artificial neural networks. In making, so what are these artificial neural networks try to do? They try to mimic what humans do. So, there are experts who can teach dogs to do various things. Certain dogs, if you say sit down, they'll sit down. Are you with me?
Yeah.
So there are people who can teach dogs. What language dogs learn? Dogs speak? We don't. So what do? They repeatedly tell them to do a certain task and reward them. They give a biscuit if it does it right. If it doesn't do, they punish it. So there is a reward punishment scheme using which you can make people learn. So that is called learning with the teacher or supervisor. But sometimes when you are a sophisticated person, so let's say you have gotten a degree in cooking, but once you know the basics of cooking, you want to be able to generate newer dishes. And who teaches you? Nobody. You never. Because you think I can fix all these things. That's how newer dishes are created. So that's called self-learning. Deep neural networks are meant to learn by themselves. So humans have the ability to be taught using a teacher. Humans have the ability to learn by themselves. Can you make the machine to be taught by a teacher? Can you make a machine to learn by itself using examples? Do you see that page? That's it. Hey, it looks like you are interested in data science.
Yes.
Please pursue. Good for you. You may be able to introduce concepts in data science into mechanical engineering, solve hard problems in mechanical engineering.
Our president has a seminar like AI in manufacturing.
Oh yeah, that's pretty good. That's pretty good.
I'm also working in that project. Okay, I wanted to make some case studies and go to some industries.
Right.
Okay.
Right.
Okay. wanted to do manufacturing without using the past days, without AI technique, and by using AI technique, how it can be improved like that.
Manufacturing is one area where AI techniques have been very broadly used. Good luck to you.
Good afternoon, everyone. Distinguished guests, honorable faculty members, my dear students, ladies and gentlemen. It is with immense gratitude and admiration that I address this crowd. I extend my sincere appreciation to Professor Lakshmi Varaham for gracing us with his profound insights into the fundamental principles of data science. Your erudition and expertise have truly enlightened and inspired us, setting a high standard for academic discourse and intellectual pursuits. Thank you, sir. I would also like to express my gratitude to our most beloved and esteemed chairman, Mr. Georgie Thomas, whose visionary leadership and unwavering dedication has been instrumental in guiding our institution towards excellence. Under your guidance, our institution has flourished and become a beacon of innovation, academic distinction in the field of technology and beyond. Thank you. To our esteemed principal, Dr. Ramesh Masi, I extend my deepest appreciation for your tireless commitment to fostering a culture of academic excellence and student success. Your visionary leadership, coupled with your passion for education, has transformed our college into a dynamic hub of learning, innovation, and personal growth. Thank you, sir. Furthermore, I wish to recognize the invaluable contributions of our academic director, Dr. Sahaya Shajan, sir, whose strategic vision and steadfast commitment to education innovation have been instrumental in shaping the academic landscape of our institution. Your dedications to excellence and your unwavering support for faculty and students alike have been a source of inspiration for all of us. Thank you. To the administrative staff and teaching faculties of our BTech section, and also the Director of Polytechnic, the Principal of Polytechnic, administrative staff, as well as the teaching faculty who have graced with their presence in this occasion. I extend my sincere appreciation for your dedication, hard work, and unwavering commitment to our student success. Your tireless efforts behind the scenes ensure the smooth functioning of our academic programs and create an environment conducive to learning, growth, and discovery. Together, collaborative efforts of the principal, chairman, academic director, and our beloved host, Professor S. Lakshmi Varaham, and the administrative and teaching faculties of BTech section have made today's event possible. It is through your collective dedication, passion, and expertise that this engineering college continues to thrive as a center for academic excellence and innovation. As we reflect on invaluable insights shared during today's session, let us remain inspired by exemplary leadership that is exhibited by our host, an unwavering dedication that is demonstrated by our principal, our chairman, and our director. May their mission continue to guide us as we navigate the complexities of AI and data science, driving forward progress and innovation for the betterment of society. Once again, my heartfelt thanks to all those who have contributed to the success of this event, and may we continue to collaborate, innovate, and inspire one another in our shared pursuit of knowledge and excellence. Thank you, everyone.